Hello everybody. This YouTube video is demonstration for a project for COE 457, Deep Learning Neural Networks with Dr. Amran. So the people who worked on the project are Amira, Luai, myself, and Yusuf. So our project is about generating techno music from using GANs. So we had a specific problem, or we had a specific uh, project, so we couldn't find any data sets about techno. So after consulting with the professor, he allowed us to generate our own data, where we got around 4 hours of techno music, of songs, techno songs, and we just cut them up into 3 second samples, and we converted the raw signals to an MFCC graph. Here's the code for doing all that. I will be attaching this notebook alongside the GAN notebook when submitting the zip file. So I just loaded everything in advance, so you guys don't have to wait. So the MFCC that we generated was of dimensions 360 and 1440. So we could not load that into Google Colab, as every time we did, it was crashing. So the largest size that we could input was an 80 by 320. CV2 just flips the dimension. It's an 80 by 320, and it worked fine. We have around 4,200 samples. So here we are normalizing our inputs, and I'm just printing them out so you guys can have a look to see the MFCC graphs. All right, and just to validate it, we just print the shape of X. You can see that we have around 4,200 images of an 80 by 320 by 3 because it's an RGB, so 3 channels. Our image shape 80 320 by 3 latent dimension, we used 200. So this is the generator model. This is all the layers for it. Here's the summary. I'll go through it slowly so you guys can look at it. All right. Here's the discriminator now. These are all the models for the discriminator. This is just a summary of it, so you guys can look at it. These are the layers that we were using. And here we're just building and compiling the discriminator and generator and putting it in the compiled network. So this is you can see it's here, it's just compiling. Yeah, so this is the summary for it. And here we are training the batch size 32, and we created the fake noise, just trying to see the dimensions, everything works out, everything's correct. Here we have 32. So we created the fake images. Since our batch size is 32, it created 32 fake images. As you can see here, we verified it by printing its shape. This is just a function for displaying images. And yeah, let me run this for 50 epochs. The minimum requirement was for 5 epochs, but 5 epochs just did not produce anything great. So I'll just run it for 50 epochs. Hopefully it doesn't take too long. 28 seconds. And as you can see, this is discriminator loss, discriminator accuracy, adversarial loss, adversarial accuracy. This is basically where we saved our previous runs. So we saved the model so we don't have to run it again to just get the results. And we use this to save the images that were produced by the GAN. Well, I'm going to run this. It's going to show you the images that are produced for the 50 epochs. To see the results, I will attach this Google Drive with the report at the bottom of it. Here's the MFCC images from the first GAN running for 20,000 epochs. And then results too, just for the second one. They look kind of similar, just this one is not as clear. All right, this will be shared with you. So let me just print the images, just make sure that nothing is going to save. Yeah, we can print this. So as you can see, these are the images. They don't look too great because it's just 50 epochs. And when we were running it for 15,000 epochs, it took us around 3 hours. Couldn't remember how much it took for the 20,000. I just left it and was checking on it every 30 minutes because Google Color kicks you out if you are not present. So this is just the evaluation. You can run it. This is doing it for the 50 epochs one. As you can see, the discriminator loss and adversarial loss dropping. I cannot run these. I can drop the epoch range to 50, but it's just basically the same thing almost. Just showing the range. This is because we only ran 50 epochs, gave me an error. We can run this too. So the discriminator accuracy is around 50%. Adversarial went up to 1 when it was around 27 epochs. Can't run this too. These are just from prior builds. This is how it was looking like. So as you can see, the discriminator loss is always at 50, but the adversarial loss was going down to 0. You can see this because of diminishing gradient. And you can see the accuracy for it, like this. Yeah. And here's the inversion. This is basically where we saved the old models, the old generated images. And here where we convert, this is the code for converting the MFCC graphs to an MFCC graph to an audio file, which is a wave. Here is the path for the results too, as I showed you. This is where the MFCC graphs are. And then we just use this function, Larbosa feature inverse MFCC to audio. We were forced to grayscale the image because this function only accepts 2-dimensional arrays. So we had to grayscale it, and it did work. We used NFFT for 200, similar to what we used when converting the audio to MFCC. So we try to stay as consistent as we can. And this is just for saving it in a final wave too. And there's the final wave that also saved. So this is from the final wave to the third file. That's how it sounds like. You can see it sounds, you can see there's a pattern for the beat, and although it's static, this is what you expect when converting an MFCC file. This is from the one the GAN has generated, and when you compare it to one of the original MFCC graph, which I have compared it, they sound very similar. So we are happy with the results, we are happy with what we have done, and thank you guys for watching the video.